Hi, I'm Messianic Michael, and a question came in from a viewer today asking us to work a physics problem. And I want to keep in mind that we do change the numbers a little bit from the question that came in so that the viewer can work the problem at home following a substantially similar method, but substituting in the numbers that they were given in their original problem. And it perplexes me because a lot of students express thoughts like, I'm just no good at math, or I can't do physics. But people of faith have the promises of Scripture which say things like, all things are possible with God, and I can do all things through Christ who strengthens me. So I encourage viewers to put their faith in the Messiah and to pray for help and assistance from Almighty God in working challenging physics problems. So let's use our IDEA problem-solving format. And just a reminder that IDEA stands for Interpret, Develop, Evaluate, and Assess. And this is our problem-solving framework, which is quite useful for lots of different kinds of physics and math problems. And in physics problems, the interpretation part, we want to recognize the general principle of physics that's going to be used to solve the problem. And we also want to draw a picture. And I've already got a picture started here. So the general principle of physics that's in play in this problem is simply free fall or constant g. We know since the time of Galileo that in the absence of air resistance, all objects are going to accelerate downward at a constant acceleration, which turns out to be 9.81 meters per second squared. So the general principle here is free fall, and most problems involving free fall quickly bring us to the kinematic equations. So when we draw our picture, let's erase a little bit here. When we draw our picture to help us interpret the problem, we have the building, and we've ascribed to the building a height of 80 meters, and we've ascribed an initial upward velocity for the stone of 50 meters per second. So continuing the interpretation a little bit here, we just sort of think about what's going to happen. The stone's going to go upward, it's going to reach a maximum height, and then it's going to fall under the influence of gravity. It's going to fall and hit the ground. And so the problem poses several questions to be answered in the process. The time that the object takes to reach the maximum height, the value of the maximum height, the time at the original height, and the velocity at the original height. In other words, it's going to go up to a maximum height and it's going to fall back through the original height. So the problem's asking for the time and the velocity on the way down as it's coming back through the initial height, and then the velocity and position 10 seconds after the initial throw. So it might be still going upward, it might be coming downward. What's the velocity and the position at t equals 10 seconds? All right, so that's pretty much our interpretation. So let's begin developing our solutions to the problem. And when you're developing your solution, you don't want to jump too quickly to the equations. A lot of students, they immediately read a physics problem and think, what equation do they need? They turn to the formula sheet, they start writing down equations. We want to think more physically about what's happening as we develop our solution. So let's think about physically what's happening, and let's make a plan, because I like to think about the develop stage more as developing a bullet point plan rather than thinking about what equations we need. All right, so what physically is going to happen as that rock or the stone is on its way upward? What physically is happening when the stone reaches its maximum height? And if you give that some consideration, what physically is happening when the stone reaches its maximum height is that the velocity is zero. The stone was going up. A moment after the maximum height, the stone is going to be going down. At the instant of that maximum height, the velocity is going to be zero. So let's compute time when v equals zero, right? You start positive, you end negative. That instant when the velocity is zero, that is the time at the maximum height. Now, at the next step, we're going to go ahead and compute maximum height. And let's go ahead, and we haven't given a coordinate system yet. So let's go ahead and as we're making our plan, one thing we need to do at this point is we need to choose coordinate system. After we choose the coordinate system, we can go ahead and take this next step and compute maximum height. Now, after we compute the maximum height, we can go ahead and compute the velocity at y equals 80 meters, because our original height is at 80 meters. But this step here is dependent on us having chosen our coordinate system that y equals 0 is at the base of the building, so the initial height is 80 meters. And that's a choice, because you could also solve this problem putting the coordinate system at the height that you're originally throwing the stone from, and then the ground would be negative 80 meters. So that's a choice that you need to define, and we define it by drawing an XY set of axes at the ground at the base of the building. Alright, and then we can go ahead and compute velocity at 10 seconds, and then we can compute the position y at t equals 10 seconds. Now in this case, the plan is very similar to the orderly sequence of steps that was asked in the question, because the question sort of led us down a path that was solving the problem in an orderly series of steps. There are lots of physics problems that you'll be asked where you'll have to formulate a recipe with more intermediate steps than may be asked in the original question, but in this case our plan is a pretty close reflection of what's asked in the question. Okay, so let's go ahead and start executing that plan, and this is the evaluate step. And we already actually executed drawing the coordinate system. So now we need to think about principles and equations. So we notice physically that at the maximum height, the velocity is equal to 0. So now this is where we finally need the equation for velocity. And if you recall from the kinematic equations, the velocity equation in the kinematic equations is that the velocity is the initial velocity plus the acceleration times the time. And now that we know that we're dealing with free fall, because when we interpreted the equation, the interpretation tells us that in free fall the acceleration is constant, it's just negative 9.8 meters per second squared. We can rewrite this as the velocity is the initial velocity minus gt. So the velocity at the instant we're interested in is 0, and it's equal to the initial velocity minus gt. And let's call this, now that we substituted in 0, this is what I'm going to call the up time. This is the time that the stone is traveling upward to reach the maximum height. So now we can solve it, add gt to both sides, solve for t up, so now we can plug in numbers, 50 meters per second over 9.8, and let's just round to 9.8. If you need to do it to more significant digits, go ahead and do it that way in your calculator. So just doing that quickly in a calculator gives 5.1 the units are wrong there. Thinking about the units, meters per second divided by meters per second squared comes out to be seconds, which is what we're expecting for a unit of time. So the time to reach the maximum height is 5.1 seconds. Okay, so let's go ahead and let's interleave and let's do a little assessment at the end of every sub-evaluation here. Does this answer make sense? Well, when thinking about whether or not an answer makes sense, you want to consider a couple things. You want to think about, are the units right, and does the number make sense? Well, if you've ever thought about the time of flight for something, and 50 meters per second is pretty fast, but things like the vertical component of a baseball in a home run, or the hang time of a punt in a football game, these are all objects that are launched upward with a little smaller than that. But a lot of times, the time it takes an object launched upward can be several seconds. But it's very rarely more than 10 seconds, and it's not too hard to throw something upward with enough velocity to be up in the air for a few seconds. So 5.1 is a reasonable number of seconds for an object to be in the air. The hang time, and of course the time down, is going to add to that. So then we think about the units, and meters per second divided by meters per second squared. Let's just do that out a little more carefully here. Meters per second divided by meters per second squared. And if you recall from your rules of algebra, dividing one fraction by another is like multiplying by the reciprocal. So meters per second times seconds squared per meter. Meters cancel out. One of the seconds in the numerator cancels out, so the unit comes out to be seconds. So when we do our assessment, the numbers make sense, the units make sense, so we can have some confidence that the time to the maximum height is indeed 5.1 seconds. Alright, so let's go ahead and evaluate to the point where we're thinking about, well, what is the maximum height? And this is where we realize we need the kinematic equation for the position. And when we're thinking about a vertical position, we like to call it y, because that's how we set up our coordinate axes. So y equals y initial plus v initial, y component, times the time, plus 1/2 g t squared. Oops, I substituted in g a little prematurely there. It's really at squared in our kinematic equation. And now we can substitute in y equals y initial plus v initial times the time plus, and now it's minus because we're substituting in negative g for a, so minus 1/2 g t squared. And we want the maximum height, so we're plugging in here the up time, the time that the stone was traveling upward. Okay, so it's going to help with our assessment if when we evaluate this, we don't just plug all the numbers in and come out with a final answer. Let's go ahead and write it term by term. 80 meters is the starting height, plus 50 times 5.1 is 255, and meters per second times seconds gives meters. And then minus, when you multiply this out, you get 127.5, and meters per second squared times seconds squared ends up meters also. So let's think about what this means physically. This is just the starting height. This is the additional height that would be gained in 5.1 seconds if there was no deceleration, if gravity wasn't acting. And this is the reduction in the height that's gained because you've got a negative acceleration going on. And when you work enough of these objects thrown upward type of problems, one of the things that you note is that the reduction in the height that you gain is always half. And this is related to the fact that the average upward velocity is half of the initial upward velocity if you start at 50 and you end at a velocity of 0. So the average velocity on the way up turns out to be 25 meters per second. So we're expecting this term to be half of this term, which helps in our assessment, so that the real final answer is just 80 meters plus 127.5 meters. So when you think about it that way, you come out with 207.5 meters. So we kind of built into our solution a way to both assess the correctness of the answer from physical considerations as well as an assessment on the expected units. So the maximum height works out to be 207.5 meters. All right, so now let's think about the time to get back to the original height. And there are different ways to come at this problem. But let's go ahead and let's think about this equation again. And once again, we want to plug in g is equal to negative 9.8. So, all right, so now we have the kinematic equation. And what we want to do is we want to solve this for the time at which the object returns to the initial height of 80 meters. So let's just keep it symbolic here to keep the math a little simpler and plug in numbers at the last step. So y initial is now y final, so we plug in that there. Y initial plus v initial times the time minus 1/2 gt squared. And what we're doing is we're solving for the value of t, where y final equals y initial. So we can cancel that out or subtract the y initial from both sides, if you will. So you end up with 0 equals v initial times the time minus 1/2 gt squared. And so now we can, let's sort of rearrange this a little bit. So minus 1/2 gt squared plus v initial times the time, and this t is squared, is equal to 0. So now let's factor out a t. So we get t times minus 1/2 gt plus v initial equals 0. And so now we've got this factored equation, and if you recall from algebra, one solution to this equation is simply t equals 0, and the other solution of the equation is the term in parentheses being equal to 0. And what does this correspond to physically? Well, t equals 0 is just the moment in time when the rock was at the original height because it hadn't been thrown upward yet, or the instant while it's being thrown upward. So that's one solution, but the solution we're interested in comes from negative 1/2 gt plus v initial being equal to 0. So now we just need to solve it for t. So we can say v initial equals 1/2 gt. So t equals 2 v initial. T equals 2 v initial over g. All right, so before we plug the numbers in, let's think about that a little bit, because if we recall, the time to get to the maximum height was just v initial over g. That's the time it takes to get to the peak. And the time it takes to get from the peak back down to the initial height is another 5.1 seconds, or another v initial over g. So when we substituted that in, t equals 2 times 50 meters per second divided by 9.8 meters per second squared. Punch those numbers into your calculator, you'll see you just get 10.2 seconds. So once you get some experience in these, if you ignore air resistance on an object thrown upward, the time going up is equal to the time coming back down to the same height, so that the time at the original height is always just twice the time going up. All right, so now we are thinking about the velocity at the initial height. So the velocity at the initial height, go back to our kinematic equation for velocity. V equals v initial minus gt. The initial velocity was the 50 meters per second, and now minus 9.8 meters per second squared times the time, 10.2 seconds. And when you plug in the numbers here, this term ends up to be negative 100 meters per second. So 50 minus 100 meters per second is negative 50 meters per second. And this is a common result also, because when you throw something up and it comes back down to the same height, in the absence of air resistance, the y component of velocity has simply reversed its direction, but it has the same magnitude. So that's our assessment on the math from our having worked enough these problems. We were expecting that. And also our assessment on the units comes down to this unit analysis. We have meters per second squared times seconds, so the units end up to be meters per second as we're expecting them. So the time of the initial height was 10.2 seconds. The velocity at the initial height is negative 50 meters per second. And now it asks for the velocity and position at t equals 10 seconds. So the velocity is simply going to be and now we're substituting in 10 seconds exactly rather than the 10.2. So this becomes 98, so it's 50 meters per second minus 98 meters per second. So it's negative 48 meters per second. And let's evaluate that. Well, at 10.2 seconds, the velocity coming down was negative 50 meters per second, and at 0.2 of a second before that, it's very close and just has a little more acceleration to go to get to negative 50. So that makes sense. And also when we think about what height it's going to be at, it's going to be not quite at back down to 80 meters. So the height we're kind of expecting to be just a little bit above 80 meters when we substitute that in. And I'll write down the equation, but I'll go ahead and leave the evaluation for the diligent student. So y is going to be y initial plus v initial times the time minus 1/2 gt squared. And so now to get the position at 10 seconds, we're just substituting in 10 seconds here and 10 seconds here. And then once you get that number to assess it, I'd compare it with 80 meters. And if at 10.2 seconds you had gone up and come back down to 80 meters, at 10 seconds you're just going to be a smidge above 80 meters, and that will provide your assessment.